So let's go ahead to hypothesis test now. So with hypothesis test, you're not trying to estimate a parameter, you're trying to measure the strength of evidence against a particular claim, the null hypothesis, and for another claim, the alternative. So you can sort of think of the null hypothesis as like the old value. Sometimes it can be no change, no effect, or you could think of it like the just by chance explanation. If there were really no effect, how likely would we be to see these results just by chance? And then whatever you're trying to prove, you want to put that in the alternative hypothesis. Okay, so the null hypothesis is always going to have an equal sign in it. So if we're talking about categorical data, it would always be that the population proportion is equal to some value. And then the alternative, what you're trying to prove, would be that it's either less than, not equal, or greater than some value. Okay, go ahead and do it for quantitative too. This one's going to be in terms of mu. So the null is that mu is equal to some value. The alternative is that mu is less than, not equal, or greater than some value. So first, notice that I'm always using parameters here. When you're stating hypotheses, you're going to use parameters. And then for the options here, for deciding what to put in the alternative hypothesis, here you're going to want to look for keywords. So it depends on what the researchers are trying to prove, what their conjecture is, what sign you're going to use in the alternative. Okay, test statistics, kind of like confidence intervals, they have this general form. So let's fill it in for categorical data first. So for categorical data, the test statistic is called Z, and our statistic is the sample proportion. We write that as p hat. The null hypothesis value, I'm going to put a little 0 next to it so you know that that's the number that comes from the null. And then I'm going to fill in the formula for the standard error. I'm going to put little zeros here too, just to remind you that the proportion that you're using is the one from the null hypothesis. Okay, for quantitative data, it's called a T statistic. Your statistic is your sample mean. You're taking the value of mu from the null hypothesis, and then again, I'm just filling in the formula for the standard error. So that's how you calculate the test statistic, and that's going to tell you how far your sample statistic is from the null hypothesis value, right? If you look at the numerator of each of those fractions, it's showing the distance between the sample statistic and the null hypothesis value. But it's talking about that distance in terms of standard errors. So how many standard errors between the sample statistic and the null hypothesis value? Okay, once you have your test statistic, you can use that to calculate a p-value. So we're going to use jump distribution calculators for this. If you have categorical data, you're going to use the normal distribution. And the defaults are already right. It's the mean of 0 and a standard deviation of 1. So you don't actually have to fill that in because that's the default. For quantitative data, you're going to use a t-distribution. Here you do have to change something because you have to put in the degrees of freedom. So that's going to be n-1. So once you've calculated the p-value, we want to be able to interpret it as a probability. So this is the probability of getting our statistic, or more extreme. The more extreme has to do with the alternative, so more extreme in that direction. And then there's always a big if in hypothesis testing, if the null hypothesis were true. So it's saying how likely would we be to get data like ours if the null hypothesis were actually true. Okay? So if your p-value is really small, that means it's unlikely we would have gotten something like this if the null were true. So that leads us to reject the null. The null does not seem to be a good explanation for our data. So in that case, we say that we have sufficient evidence to conclude the thing we were trying to prove, which should be the claim that we put in HA. Okay? Whereas if your p-value is large, that means this is a likely outcome even if the null is true. So in that case, we fail to reject the null. Okay, and if you fail to reject the null, you can't really conclude anything at all. So here you have insufficient evidence to conclude, and again, you were trying to conclude HA. That's not going to change. Okay, so the role of alpha is a cutoff for your p-value. It's deciding how small does the p-value need to be before we're willing to conclude the alternative. Alpha is relevant because it helps you figure out whether you're going to make it easier to reject the null or harder to reject the null. In other words, how much evidence you're going to require before you're willing to conclude the alternative. So if your alpha level is higher, a higher alpha means that it's easier to reject the null, right? Because you reject the null anytime your p-value is lower than your alpha. So the higher your alpha is, the easier it is for your p-value to get underneath. Okay? Whereas a lower alpha makes it harder to reject the null. And this is also related to the types of errors that you make, right? Because a type 1 error occurs when researchers reject the null, when in reality the null hypothesis is actually true. So if you make it easier to reject the null, if you make your alpha level higher, that's going to mean more type 1 errors. A type 2 error occurs when researchers fail to reject the null, when in reality the null hypothesis is actually false, or we could say that the alternative is actually true. So if you make your alpha lower, that's good because you have fewer type 1 errors, but the trade-off is that you have more type 2 errors. It's going to be harder to reject the null. It's going to be harder to prove what you're trying to prove. This is also related to the amount of evidence that you have. So just in general, if we want strong evidence against the null hypothesis, that's going to happen when the sample size is large, right? More information, more evidence. And when your sample statistic is far from the value in the null hypothesis. Remember, when we talk about strength of evidence, we're always talking about evidence against the null and for the alternative. So the further away from the null hypothesis you are, the stronger your evidence. And then you can translate that to test statistics and p-values. So strong evidence is going to give us test statistics that are far from 0 and p-values that are close to 0.